Good afternoon, everyone. Today we'll be talking about signal processing in electrochemistry with Python, applications to the US opioids crisis. So first of all, I always like to start with this basic question: why are we here today? And I think we all have different interests and motivations for being here, and I find really exciting that this event gets everyone together to discuss about Python and about different open source projects and ideas. And with that, I really wanted to thank the organization for hosting this event. So I would like to call for a quick round of applauses to them. Thank you very much. Yeah. And with that, I would like to start my talk. Just first talking a little bit about me. My name is Rodrigo. I'm from Salvador, Brazil. That's a photo of my city. So I definitely feel a little bit of home in Austin due to the weather, the beautiful weather. As I currently live in Pennsylvania, my background is in chemistry, but I currently work as a QA engineer for a statistical software company. And I'm really interested in the intersection between statistics, chemistry, and public policy, and how we can use Python and data analysis in general to understand and improve the world. So with that, I would like to provide a quick overview about the US opioids crisis, in which fentanyl has been a major source of concern, although it's used for severe pain treatment, and it is also used for recreational purposes. It's 20 to 50 more times more potent than heroin, and 50 to 100 more potent than morphine, and it's often consumed in conjunction together with other drugs, and this is a major source of concern from a detection standpoint. In terms of what happened in the US in the past 25 years, has been different waves of drug overdoses due to different types of drugs. The latest wave, labeled as wave 3, is due to synthetic opioids. So that's the focus of my talk here. And the US spends a lot of resource, a lot of money dealing with that opioids crisis. It's estimated that in 2020 it was $1.5 trillion. So this is a major concern in terms of public health and public policy. So just for context, I'll get really quick through this part of chemistry because I know that's not the main interest here. But in the middle, we have the fentanyl molecule. And one very important aspect of fentanyl is the presence of analogues, meaning you can change the functional groups to different types of functional groups, originating other types of drugs, essentially. And that's what we call analogues. So they are structurally very similar to fentanyl, but they have different structures depending on what you modify. And these are just 3 examples, but in reality, there are infinite possibilities, making it really difficult to target the fentanyl analogues, for example. And just as a matter of perspective, fentanyl, the lethal dose is really low. And comparing with a dime, we can see that a little bit of the powder can kill someone. And carfentanil is an analog, meaning it's with a modification of a chemical group, and even less of that is considered lethal, making it a really concerning for many states across the United States, including Texas. And in terms of recent trends, we can see that opioid overdose deaths due to opioid has been on the rise in Texas as well, just like in many other states. And that when it comes to overdoses in general, oftentimes fentanyl is mixed with the drugs that caused overdose. So we can see that it's almost half at this point of overdose deaths have fentanyl present in the mixture with the other drugs. Once again, making it really difficult to target and detect fentanyl specifically. So in terms of current methods of detection, there are centralized methods that are done in the lab, as well as decentralized methods that are inexpensive, portable, and can provide rapid results, but they are not very specific, and they don't have the desirable detection limits that are really important for fentanyl and other opioids. And that's when electrochemical biosensors can play an important role and can become an important opportunity for detection. And there has been a lot of development in research in terms of flexible wearable electrochemical sensors, electrochemical test strips, using carbon nanotubes to enhance sensing, as well as novel approaches to electrochemical data analysis. And there are different types of electrochemical data that can be obtained from experiments. Here, we are going to focus on cyclic voltammetry. And the basics of cyclic voltammetry is that you apply a certain potential, you sweep a certain potential between different limits. And as you do that, you obtain a current response that allows you to have the chemical signature of the substance. And the expectation of every electrochemistry is to obtain a duck-shaped curve it's literally a duck-shaped curve for the electrochemical signature of a substance. In reality, it's much more complicated, as I will show, but essentially that electrochemical signature can provide important information about the concentration of the substance that you have, the type of interactions that it has in the system, and so on. In reality, you often get noisy signals, overlapping signals, which make it really difficult for detecting and quantifying the substance that you have. And oftentimes, the data that you get can be very messy, and experiments are really expensive to run. So before discarding the messy data, we could use Python to enhance signal processing. And that's what I'm going to introduce the idea today, essentially in terms from plotting to processing the data to performing optimization, as well as statistical analysis, all with Python. So I will start by mentioning the main tool that I'm going to use for the first set of scripts, which is the Savitsky-Golay filter, which is present, which is available in the scipy.signal library. And it can be really helpful to smoothen messy signals. And there are two very important parameters that I'll just mention briefly, which are the window size and the polynomial order. Basically, when you try to smoothen a signal using that type of filter, you want to get to specific values that are going to yield the best smoothing of the function. And you, at the same time, want to prevent overfitting of the curve, because in that way you would essentially get rid of your signal. So it's a very complicated problem that Python can really help with optimizing. And the benefits of applying that filter is noise reduction, preserving the main features of the signal, as well as accurate analysis of the system. So I'll go on with the first script. I think the timer is not. Yeah. Okay. So for the first script, the main purpose was to demonstrate how the filter can help optimize the cyclic voltammetry signals with specific parameters. So these are the tools that I used. As you can see, the scipy.signal is the most important tool here that comes really handy in that context. And the CV data I got from a publicly available resource. And then for this first script, I decided to specify different combinations of window sizes and polynomial orders, as you can see on the left of the slide. And then I applied different random noise levels to the signal, and then I attempted to reconstitute the signal. So that's the idea. Those are just a few remarks of things I did in the script. If anyone is curious, you can check on the GitHub library that will provide, GitHub repo that will provide in the end. And again, essentially, we're interested between minus 0.5 volts to zero 0.2 because that's what the potential window that was applied in the experiment. And yeah. So we averaged the mean squared error values just for future statistical analysis. And we stored the results in like Pico files just to make it easier to compare later with the hyperopt script. And Pico is just an easy way of storing the results and recovering them later for post statistical analysis. And that's what I find really helpful. So here's the for the data. First with 0% noise just as a control, and then 10% noise. You can see here that in blue, we have the original CV data. In red, we have the noisy CV data. And then we have in green, the attempt to filter the red signal without knowing the blue signal, of course. So we are essentially trying to recover the signal by applying different parameters. Here we have 4 different groups of parameters, and we are trying to essentially recover the signal. So that's the main task here. And as we increase the noise, it becomes increasingly difficult to recover the signal, of course. And so I did all the way from 10% up to 100% as control, essentially. And then I compared the results for the 4 different models containing the different parameters for window size and polynomial order. And the goal here was to understand if there was significant difference between these 4 models. And it was concluded that they were not statistically significant, meaning that any of the 4 models were satisfactory when it comes to recovering the signal up to a certain noise level, of course. And then we go to the second set of scripts, which is using hyperopt to optimize the parameters without the need for me to guess those parameters, but rather just letting the hyperopt search to do its job. And here, the type of algorithm that was used was tree structure parsing estimator. And just to provide an idea of what is behind this algorithm, it's essentially as if you're navigating through a tree, and instead of going through every branch, you just go through the branches that have higher probability of being the ones that provide you the best results and the best expected improvement, which is shown here. So you are essentially finding the balance between exploration and exploitation of specific branches in the tree. And you can choose different number of trials. As you increase the trials, of course, you increase the computing time, and you can increase the accuracy as well. But for here, we just decided to do with 20 trials only. And this is the script, part of the script that I used. So we define the search space. We put for the window length, it's always odd numbers between 5 and 101. And for the polynomial order, always odd numbers between 1 and 7. And we store in the Pico files. And these are the results for 0% noise, then 10%, 30%, 50%, 70, up to 100. And again, here, the main goal is to recover the signals, the original signals, using hyperopt instead of just guessing the parameters. And again, we compare. No significant difference between the 4 best models that the hyperopt search identified. And then comparing the script 1 with the script 2, there was some interesting thing, which was there was no statistically significant difference between the guessed parameters versus the hyperopt parameters, meaning that we have three ways to approach optimization here. We can guess the values, which was what I did initially, that yield the lowest errors, which is very difficult. Or we can conduct trials across all search space, which can be a waste of computer resources and time. And lastly, we can use hyperopt to optimize the gases and to provide good results for the optimization. And of course, it depends on the context, but in this context, it can come really handy. And then another method that is useful and that's very prevalent with scipy is using discrete Fourier transformation in order to separate between signals of overlapping substances. And here I would emphasize the advantage of using DFT in this context, because as you obtain different harmonics, you can, depending on the order of the harmonics, you can see the differences between the signals. And as an example here, I will show you how Fourier transform can help dissecting between these signals. So this is part of my script. And just to show here what I did was that in green, we have the original data from cyclic voltammetry. In red, we have the interfering substance data. So as you can see, it's in a similar potential range, similar shape. And in blue, we have the combined signal. So essentially, as you do an experiment, you would only obtain the combined signal. So it would be very difficult to distinguish between the substances. And as you perform Fourier transform, you can essentially obtain so we would obtain the combined Fourier transform. And as you accumulate data from other experiments, you could have essentially a database that you can use to help you dissect between interfering substances. So here we can see in the fifth harmonics, we can see that we can essentially dissect the signal between the original substance and the interfering substance, making it really helpful for separating mixtures, essentially, their signals. Yeah. Yeah. And lastly, the last method I would like to highlight is the discrete wavelet transform. The way I like to see it, it's almost like a hand in which you want to see the details of the palm of the hand without losing track of the shape of the hand. So that's the main idea behind it. So you want to decompose the signal, but if you decompose too much, you're essentially losing the shape of the signal, in which it wouldn't be helpful. So here's part of my script. I used a specific algorithm for that, which is DB4, and it allows for compact support, orthogonality, and vanishing moments, which these three characteristics are really important because it helps to dissect the signals without losing their main features and characteristics. So here's an example: original data, noisy data. We increase the noise up to 100% just for control purposes. And then as let's say at 10%, for example, we can notice how as you increase the levels of the coefficients, we can see that we start losing track of the original signal, meaning we can no longer find a correlation between the original signal and the noise signal. So we are essentially transforming the noise signal that we saw in the first curve that we can't really correlate with the original signal into wavelet transforms, which then resemble the original target signal. As we increase the noise levels, though, it's very evident that it becomes very difficult to reconstitute the original signals at the higher levels. So that's one of the main challenges with that. And then, yeah, so those were just a few methods. And of course, I had to go really fast through the whole presentation, but I think the main takeaways here that I would like to highlight is how different signal processing techniques, together with Python, can really help to solve problems that are related to data analysis and data processing, especially in the context of signals. And the reason why this is very relevant in electrochemistry and in science in general is because, as I said before, experiments are very expensive, and oftentimes data is pretty much discarded, thrown away, because we think it's not good data, but in reality, maybe we are just lacking the resources and the skills to process the data in an effective way that can provide better insights about what is happening with the science. And the way it can help in general with detection of opioids is because there is an increasing need for more sensitive and selective sensors. The reason for sensitivity is due to, you saw before, how low the concentration is for fentanyl, for example, to be lethal. So we need very sensitive sensors. And the reason why it needs to be selective is due to oftentimes being mixed with other drugs. So you need to be able to distinguish between fentanyl, carfentanil, heroin, cocaine, and so on. And ultimately, I'm really interested in finding problems and that have to do with like issues of societal interest and how we can use data to better understand and improve the world. So that's why I decided to do this talk here today. And yeah, those are some references in case anyone is interested. That's the GitHub repo that anyone can check. And if you want to get in contact, that's my LinkedIn. And yeah, that's all. Thank you very much for